Okay, so videos for week 8 are going to be about soil reactivity, which is all about soil pH. And so today in video 8.1, we're going to talk about soil reactivity and soil pH and soil acidity. And so there are going to be 4 videos in this week's lecture content. And this week's content will be on midterm 2 on Thursday. So we talk about acidity and the pH scale, and just to remind you guys that pH is equal to the negative log times concentration of protons. And it's a log scale, which means that for every unit of change between 0 and 1 is 10 times more acidic. And so we can sort of see that at neutrality is about 7, and as we decrease in numbers, we get more acidic conditions. So the concentration of protons is increasing the closer we get to 0. And as we go from 7 to 14, the concentration of protons is decreasing. We say that it's getting more alkaline. And you can see here there's a number of different materials with different pHs. And one thing I will point out is that extreme acidity, so a pH of 1, is very dangerous, very corrosive to your skin, very dangerous, but an extreme alkalinity, so a pH of 13 is also incredibly dangerous as a corrosive. We'll give you some ranges of pH found in soils. We can see here that we have 7, our neutral zone here. So our calcareous soils and sodic soils have a high pH, meaning they're alkaline. So these are the soils we find in Alberta. Then we can have some humid region arable soils, so that would be found in areas like Quebec, so pH getting more acidic down to about 5. And our forest soils, in British Columbia, Alberta, Ontario, and Quebec can have a pH range between 6 and 3.5. And we can have acid sulfate soils too, and so our typical range is in soils from about 3.5 up to about 10.5. And so soil reactivity. So acidity in soils is dynamic. And so soils are said to be reactive. And depending on the nature of the parent material and the nature of cations present, we have different pHs in soils. And so there's a couple things to consider about soil reactivity. The first is that there are acid cations in soil, are protons, and aluminum ions. And we'll see why that is in a moment. And our basic cations in soil are sodium, potassium, calcium, and magnesium, as I mentioned before. And there's an environmental effect. So not only is there an effect of soil parent material and the types of cations that are present, but there's also an effect of the environment on pH. And so in wet climates, generally produce a lot of protons, and base cations are leached. And so therefore the soils become acidic. And this is typically what happens in BC and Quebec. And then we have dry climates where there's an accumulation of base cations and they become alkaline over time. And this is typically what happens in Alberta. So we have two things going on. We have both the parent material causing acidity and the climate, which is compounding that acidity. And if we look at this graph, we can see what the relationship is as we increase pH from about 3 to about 8. So this is, within the natural region of pHs found in soils. And remember that anything higher than 8, there's negative plant growth higher than 8 and negative plant growth below a pH of 3. And so if we look on the y-axis, we have the percent of the cation exchange capacity that is being satisfied by these different acidic and basic cations. And so what we can see down here is that in our lower pH range, we have most of our cation exchange capacity being satisfied by aluminums and this exchangeable protons down here. And as we increase our pH to about 7, what we find is that our cation exchange positions are being dominated by base cations at these higher pHs. And so we can define a couple terms about acidity in soils, and these are active, exchange, and reserve acidity. And we can talk about why aluminum is an acidic cation in soils. And so active acidity is protons in soil solution which are measured with a pH meter. Okay, and so that's these guys over here. So this is number 1. So these are just protons, these little white ones are protons floating around in solution. That is our active acidity. And our exchangeable acidity represents aluminum and protons on exchange sites, which is measured by extraction. So this is measured in water, and this can be measured in calcium chloride, where you're exchanging some of the aluminum and protons on exchange sites to look at the exchangeable acidity. And so this is exchangeable acidity is over here in this region. So this represents aluminum and hydrogen that are bound in the cation exchange capacity of the soils on this sort of double ionic layer. And then we can talk about residual acidity, which is aluminum and hydrogen bound in non-exchangeable forms on clay surfaces and is not really measurable and is only enters the exchangeable acidity slowly over time. But this factor is what leads to buffering capacity of soils, which is the soil's ability to resist changes in pH, and we'll talk about in the next series of videos. And the last thing on this slide that I want to touch on is why aluminum is considered an acid cation. And it's basically because it has the ability to dissociate water. So in an aqueous environment like soils, there's always water present. There's always water present in soils. And so aluminum will cause the dissociation of water, and it'll strip off and it'll bind with this hydroxyl group and it'll free this proton in solution. And it does that in 3 stages. So the dissociation, so aluminum cation can dissociate 3 molecules of water, thus releasing 3 protons for every 1 cation of aluminum. And so it has a very strong effect on soil acidity. So that's why aluminum is an acid cation.